Today what we're going to work on is a technique for solving differential equations. If we know a solution already, if we know one of the solutions, can we find another one for the second order differential equation? And it's called reduction of order. And I am going to tell you the steps that go through it are interesting. The concept, simple. The steps can be a little bit messy as we go through there. So the general steps are, 1, we assume that whatever solution we're given actually is the basis for our second solution. So if we know our first solution is y1 or y sub 1t, then our second solution is some other function v multiplied by the y1t. Okay, so for example, if one of our solutions is x, and we end up solving for v and we get v to be also x, then our second solution would be x squared. That's the very simplistic part of that. It's not quite that easy.
But if v is a constant function, then the dependent solution. So
that's true. That I was just trying to give you general. Yes, that is true.
But v can't be a constant. V has to be a function of t.
V is a function of t, or v is a function of x. Can it not be a constant though?
If it's a constant,
then they would just be, yes, they'd be linearly dependent. Yep. Now, what we're going to do is we are going to plug that equation in. So we're going to make the assumption that this is our solution, and we're going to plug it into our differential equation and solve for v. Okay, so keep in mind, my whole goal on all of this is to figure out what v is, or this v of t or v of x, whatever the function is, so that then I can write my second equation. Okay? I'm going to highlight the main, this is hard to put into, you will do this first and then this second and this third. All the other equations we've had so far kind of fit that pattern, like do this, then this happens, then do this. Reduction of order is not quite that way. So what I'm going to do is I want to walk through an example to kind of go through the steps. And as we go through the steps, I will highlight the important parts and like the parts that I'm like, yes, this is what you're going to do every time. But it gets a little bit messy. We'll just put it that way. It's fun, but kind of messy. Kind of messy. Okay. So this says to find a general solution to the equation 2t squared y double prime plus ty prime minus 3y equals 0. So second order linear differential equation. We know that one of our solutions is y1 of t equals t to the negative 1. If I want to find a general solution, I'm looking for something that is the superposition of two solutions. When we did the repeated or the real distinct roots, we did something like c1e to the rt plus c2e to the rt. That's what I'm looking for, is that type of solution. Okay, so the first thing I'm going to do is I am going to assume that my second solution, that's why I'm going to notate it with a y sub 2, is going to be v of t multiplied by y1 of t. Now for us, I'm going to simplify this as much as I can because I don't want to deal with crazy notation. So y2 is going to be v times some t raised to the negative 1. That's what I'm assuming my second equation is going to be. Now, my goal for this, my goal here is to solve for v. Just so you know what we're trying to get. My whole point of this is to get v. Okay. So in order to do this, the next thing that I'm going to do is I'm going to take this solution here, this y sub 2, and I'm going to work so that I can plug it into my differential equation. Now, in order to be able to plug it into my differential equation, what I'm going to do is I'm going to take all of my derivatives. So if I have, I'm just going to go with y now. We're going to assume everything we're working here is y sub 2. But if we have y equals v times t to the negative 1, and I want to substitute this into the differential equation, I need to find y prime. And y prime is going to be a product rule because v is a function. So I've got the derivative of v times t to the negative 1 plus v times the derivative of t to the negative 1, which would be negative t to the negative 2. Let's clean that up just a little bit. V prime t to the negative 1 minus v t to the negative 2. Okay, so I have my original function, which I need. I have my derivative, first derivative, which I also need. But in addition to the first derivative, I need the second derivative, so now I'm going to find that. So y double prime, and now I've got multiple products. Y double prime. Okay, derivative of the first times the second plus the derivative, well, this is the exact same problem we just did. So there is my derivative of my first. So,
Shouldn't there be a v prime there?
yep, that would be v prime. Thank you. That is that derivative. Now I'm going to take the derivative of the second. Let's change that so it looks like a v prime. I'm going to take the derivative of the second part, but it's minus, so I'm going to put it in parentheses. So then I have derivative of the first times the second plus the derivative of the second would be negative 2t to the negative 3 times the first. Oh, I said t to the negative 3 and wrote t to the negative 2. Whoops. Okay, so let's combine like terms because I think we have like terms here. Yeah. Okay, so this is the derivative of that piece. All right, so let's go back and combine like terms. So we know our y double prime is, let's see here. We have v double prime t to the negative 1 minus 2 v prime t to the negative 2. That'll end up being plus 2t to the negative 3v, or 2v t to the negative 3. I don't care which one it is. Whew, messy. Now you see why I left you more room. Okay, so this is my second derivative that I need here. So now what I'm going to do is I'm going to take each of those expressions, or those equations, y prime, y double prime, and plug it into my differential equation. Oh. Okay. So, I am going to take each of these. I gave you the entire French side. Okay, there's a reason. Janet, how big did you write?
There's still some.
Okay, here we go. Let's plug it in carefully. So 2t squared times y double prime. Ooh, v double prime t to the negative 1 minus 2v, prime, t to the negative 2. I'm going to switch the v. That's terrible. Okay. So that's my second derivative. Now my first derivative will have a t out front, and then we will have v prime t to the negative 1 minus vt to the negative 2 minus 3 vt to the negative 1. Okay, so we have our y prime, and our y double prime. And this has to equal 0. Well, we've got to solve the equation. Okay, so I'm going to try to make this as clean as possible at this point. And it actually cleans up pretty nicely, I think. So here, if I distribute my 2t squared in, I would be left with 2v double prime t minus 4v prime plus 4v t to the negative 1 plus t times t to the negative 1. That goes away. So I'm just left with v prime minus vt to the negative 1. I got to get my negatives brain working here. Minus 3vt to the negative 1. And now let's combine like terms. Because I think I have like terms here. V prime. Just v prime. Okay, that goes. And then vt to the negative 1. I've got several of those. They all cancel? Yeah. Yeah, they do. Okay, so we've got 2v double prime t minus 3v prime equals 0. See, it wasn't that bad.
So is that a general solution now?
No.
Oh.
Because remember, what's my goal? My goal is to find v. Oh. Now comes some more work.
You have to do like, what is it called?
So that's not even our second solution.
No,
Integration.
we do have to make a substitution. We're going to make a substitution. Okay, now remember our goal was to solve for v. And at this moment, I've got an equation that's got a second degree v and a v prime. Well, this process is called reduction of order. Right now, my order is 2. I need to come up with a way to reduce the order, reduce that order of the derivatives there, in order to solve.
Could you just make one of them 0 and another one?
Wouldn't that be nice if we could just make one 0?
Oh, make one of them.
No.
Two already like
Prime.
trivial solutions.
Say what?
Two is already like unknown trivial solutions.
0 is a trivial solution, yes. To reduce the order, this is what we do now. So we went through and we assumed my solution was going to fit the pattern of some function v times the solution we were given. And then what I'm going to do is I'm going to plug those into the differential equation and simplify. Well, it creates a problem that has too high of an order for us to deal with, or that so we need to reduce the order. We are going to reduce the order, we're going to make a substitution. Here comes another variable. Sorry. We are going to let some other variable, W, R, S, M, T, K, I don't care what you use. Don't use T because it's already in the equation, sorry. X if you want. But we're going to pick another variable and we're going to let it be V prime. Now, here's why we do this. We can solve first order differential equations much easier because we can separate them. They could be linear, they could be exact, there's lots of ways we can do first order. So our goal is to bring it down from a second order differential equation to a first order differential equation. Yep.
Could you do what we did on like Monday and Tuesday with this one, or would it not work?
If we could have a characteristic equation, yes, except no. These aren't constant coefficients. What we dealt with on Monday and Tuesday were constant coefficients, so not function coefficients. Whereas here we have the function 2t in front. So no, good thought. Okay, let's say you ended up with just constant coefficients, then yes. Chances are you're not going to. Sorry. So I'm going to let w equal v prime. So then dw dt equals v double prime. Here's why that's helpful. When I go and plug this in, we end up with 2t w prime, I'm just going to call it w prime rather than dw dt, minus 3w, I might actually go call it dw dt, sorry. We're going to separate it anyway, so it may as well look pretty. Minus 3w equals 0. Now this becomes a pretty simple separable differential equation. Now I will tell you the work that follows it is a little bit messy, but we can do it. I can separate this. If I separate this differential equation, well, let's do some work first because it's not quite there. dw dt, let's call it 2t dw dt equals 3w. And now let's work on separating this. So if I move my w over, I would have 1 over w dw. And then this would be 3 over 2t dt. Remember, we want to take as little, okay, our ultimate goal is to solve for v. But the substitution that we just made is, let's let w equal a derivative of v. So now my goal is to get w by itself. So,
We did it.
almost. My goal is to get w by itself. So I'm going to take as little with the w as possible. That's why the 3 stayed on that right-hand side. When we separate, if what we're trying to solve for, take as little with it as possible. Now you understand why I gave you such a big piece of paper, right?
Aren't you over the other thing?
Say what?
Go over to the other side and do the same thing again.
You do. Okay, I'm just going to keep scrolling.
Yeah, I can't.
I know you can't scroll. Go up to the next side. Make columns. Chandon, you wrote too big. Okay, I'm going to integrate both sides. Because my goal is to find v, and to find v, I need to find w first. So, taking the antiderivative, we'd get the natural log of the absolute value of w equals 3/2 times the natural log of the absolute value of t plus that constant of integration. Okay, so my goal is to find what again?
W and then V.
V by extension w, right? So, what I'm going to do now is I'm going to solve for w. To do that means I'm going to exponentiate both sides. Here's why. On the right hand, that's left. I do know the difference most of the time. On the left-hand side, we get the absolute value of w. On the right-hand side, we would get e to the 3/2 natural log of the absolute value of t plus c. Now, typically what we would do is use our properties of logs to say, okay, let's bring down that c and let's make it e to the c. Well, e to the c is just a constant. It's a c. Now, when I solve this, to remove the absolute value, if you remember, we would do plus or minus c e to the 3/2 natural log of t. Okay, can I do more work? Can I simplify this any?
You could bring down the T something.
Can't you cancel out the?
Right. We can deal with this portion right here. Remember, to have a 3/2 in the front, oops, is really just t to the 3/2. So this would be w equals plus or minus c t to the 3/2.
Would there be an absolute value sign around the t or no?
No, we can bring it down.
Why?
Because your cube, well, probably it should stay.
We already said
But we're going to anti-differentiate it anyway, so it's going to go away. How did I what? Plus or minus. We can ignore that at this point. We can you know what we can do? Rather than ignoring it, let's just let that constant absorb the plus or minus, because really, if I have a constant in front and it's meant to be negative, it'll end up being negative. And if it's meant to be positive, it'll end up being positive. All right. Now here's the problem. Remind me again what I'm trying to solve for. V. What do I have?
W.
Well, I'm closer, right?
But doesn't W equal V prime? So can't you just do that and take the other row?
Right. So if W equals V prime, then what we know is that V prime equals C T to the 3/2. And maybe, since this is separable as well, maybe we call this, well, let's just take the antiderivative now. Let's call that. So this would really be, what we're really doing is we have dv equals ct to the 3/2 dt, and then we're taking the antiderivative. Because v prime is dv dt.
Oh yeah, but like when you take the derivative of V prime, don't you just get?
I didn't take the antiderivative.
Yeah, when you take the integral of V prime, won't you just get V?
Yep. And the antiderivative, c is a constant, so I'm going to go up a degree divide by that degree, which means I'm going to end up multiplying by 2/5. See? Do I need the 2/5?
No.
No, but I do need another constant of integration, so I'm going to call it k.
Or we call it C2.
Or plus c2. You could do plus c2. So here's what we have. V equals some constant times t to the 5/2 plus some other constant. Let's not change it. But I'm not done. But I do know V. I do know V. But here's the easy part now. Now what I'm going to do is plug this into y2. Y2, remember, is V
I actually like these better than
times the t to the negative 1,
What was Y2 again?
this is the first thing.
Oh, the first thing we wrote, yeah.
which means Y2 is ct to the 3/2 plus kt to the negative 1.
kt to the negative 1 disappears because it's already a given solution.
Yes. Now, hold on. Let me explain why. You are correct.
You're getting too far ahead of us.
Okay, but now, the question asked me to find what? The general solution.
God dang it.
Okay,
Come on.
remember the general solution is the superposition of y1 times some constant plus y2 times some constant. We know y2. We also know y1 because that was the original problem. So now if I were to give my general solution, we would get y equals some constant times the original equation that they told us about, t to the negative 1, plus some constant times the y2 that we just found. I am going to clean this up because it's a bit messy. I got a lot of things happening in here. So let's clean it up just a bit. Okay, I can't really do anything with this just yet, but let's talk about this y2 term. I have a c2. Sorry, I'm recording a video, so I got to point to it on the screen too. I've got a c2 that I'm going to multiply in. So really I have a constant multiplied by a constant.
Another constant.
So I just have a constant. Do I need to give it a specific name? Not really. You may have a professor in college that's pretty adamant about the notation of the constants. I'm not going to be. I don't think it's necessary. I'm sure it is. I'm sure somewhere it's necessary. Anyway, I'm going to multiply these two together. Then this constant times this is also just a constant.
There's another but different constant.
But then look at this real quick. If we notice, this is a constant raised to the t1. This is a constant raised to the, sorry, that's not what I meant to say. This is a constant times t raised to the negative 1. This is a constant times t raised to the negative 1. Those are like terms. So really what I just have is some constant times t raised to the negative 1 plus some constant, we'll call it c2, times t raised to the 3/2. And this is my general solution.
How did you go from Y2 to Y to the general solution again?
You don't feel like it's worth it? How did I go from y2 to the general solution? Because the general solution is always a constant times our first solution plus a constant times our second solution. This is our second solution.
How do we know there isn't a third solution?
Well, we're on a second order differential equation.
Oh, yeah, that makes sense.
Could I just, for the next ones, do like C1 T to whatever is in
And then you-
the second part of the first equation, and then take the coefficient of the first one and divide it by the last one?
What if that doesn't work?
So the C2 is
What if it does
the
work?
first thing.
Maybe we'll name something after Jack.
The C2 in the second to last equation up there is different than the C2 in the
Yes, truly this should probably be called something else. I mean, if we were to be more accurate, this C right here would probably be like C, I don't know, what are we on? C4, 16, 27, I don't know. It is a different constant.
But it could just be a different.
Yeah. Yep.
You know what?
Terrible? Kind of.
It wasn't like
It's just
super
a
difficult, it was
lot.
very algebraic.
Very algebraic.
There's
Lots of
another
step.
one.
Solution. So let's try this one. And the very first step is to assume that y2 is some function v times the solution we were already given. So we're going to start there. So try it.
But what if that's...
I'm just going to give you the solution up top just so you can check your work in case you're...
Oh, yeah.
Why do I have so many dots?
It does follow my rule.
But that's not what you said earlier.
I got CT squared.
What happened to your
Wait, no, this is a negative. Where did
Keep
you get
working. I'm
negative?
just going to go ahead and start doing some of the basic work.
You have a negative 4 ln t plus c.
I have negative 2.
No, they're both.
What?
How do you have negative 4? Where'd you
Go back to, you have your 4 and your, before you separate it, you get for your v equation. Yeah, because you get v double prime t cubed plus 4v prime t
You
squared.
get a 4.
From 2v prime t squared plus 2v prime t squared.
Where's the second one?
Bryce, you showed up.
Wow.
Hello, Smith, man.
It's a bad day then.
Yeah, he said
This is the first problem.
Yeah, I like you.
You know it's bad when there's two problems on a note.
Yeah,
Usually
that's a
it's
little,
gonna
that's a little frightening.
I plugged
I
it.
thought my phone was too big. I wrote too big and I wrote really small.
I mixed one of these, there's another one.
Where did they come from? What's the answer to
I got a question.
I don't know if I remember off the top of my head, so let me look.
I don't know.
Because it comes from the white paper.
All right. Substituting in, combining like terms, we get...
Hey, I got that.
All right. So then what did you do?
Let W equal V prime and then V does let dW or dt equal d double prime.
Okay.
The t get cubed.
Dude, t squared times yeah, it should be a t squared up
This should be, sorry, this should be a t squared. Oopsies. That was a big... Sorry. Plugging in, we would get t cubed dw dt plus 4t squared w equals 0. So I'm going to separate everything as much as I can. So I get dw dt equals negative 4t squared w over t cubed dw dt negative 4w over t. I'm gonna move up here. I get 1 over w dw equals negative 4 over t dt. We get that far? We good? Okay, so we're gonna integrate now. So we get the natural log of the absolute value of w equals negative 4 natural log of the absolute value of t plus c. I'm going to exponentiate that. So I get the absolute value of w equals, I'm going to cheat just a little bit. Are we okay with that? So I get c e to the natural log of t to the negative 4, which means I get w equals some constant t to the negative 4.
Yeah.
Which means dv dt equals ct to the negative 4. And now I'm going to anti-differentiate this. I'm going to move the dt over here. So then we get v equals, go up a degree, divide by that degree. So I get c over negative 3 t to the negative 3 plus k. I'm going to absorb that negative 3. So my y2 is really v, this ct to the negative 3 plus k, times the t we already had. So y2 is ct to the negative 2 plus kt. And then my general solution is the superposition of both. So c1, my original solution was t, plus some constant 2 times ct to the negative 2 plus kt. This part right here will get absorbed with this part. So really my final answer is just y equals c1t plus c2t to the negative 2. Are there any questions on that?
Wait, I got lost somewhere.
Where'd you get lost?
Well, I got to the ct to the negative 4 equals w, and then I differentiated. I think I differentiated wrong, but I got it right now. So then after you differentiate, you just set it all equal to y2, and then you multiply out. Okay, that's not too bad.
Yeah, because remember from above, y2 is v times t. This is our v. So we're multiplying v times t.
Yeah, so that would just be t.
All right. Any questions?
Wait,
Amok.
I'm just confused.
No idea.